Hello viewers, welcome back to the Multimagic channel. Myself is Funny. Hope you all had a great Diwali. I had a great Diwali. I spent time with my family members and kids, and it went good. So let's start today's video. It is about audio basics. So as we promised in the last couple of videos, we said we'll be starting a series related to audio as well as video, and then some mini projects associated with audio and video. Okay. So we will be kickstarting this audio series video now. So with the first video called Audio Basics. So now let's jump into the agenda of today's. So first I would like to convey my motivation why we are doing this particular video and what is the main motivation behind it. And also I want to tell a little bit about what is audio in very layman terms and what is sampling. And also we'll go through different digital audio terminologies, and we'll also talk a little bit on Nyquist theorem, and also we'll see what is the need for codecs, and also we'll just have an overlook on different types of audio codecs and what are the FFmpeg APIs used for audio processing. So okay, so let's start this. So the main motivation for this video, we had a feedback from our subscribers as well as viewers, as they could able to follow our journey, and also they could able to see the amount of hard work we are putting, but they are not able to actually uh, get few basic details. I mean, like what is audio, what is video, what is the sequence, actually what is the process, like basic terminologies and concepts were not scattered in the earlier videos, because we are majorly focused on our journey. So now we would like to cover those details. So first thing is, you can do anything. So why I have put this is because, to learn anything, especially on audio and video side, in fact, to learn anything, to build a knowledge on any domain, so you need to, it's not like that you need a very good sound domain knowledge on that particular thing. Let's say if you're doing some programming or networking, if you're doing programming on some other embedded domains or other things, it's not like that you should know the complete A to Z of that domain. So you need to start with a very minimal domain knowledge in that. Okay, that is my point of view. Of course, as you learn across, as you spend more time on that, you will be gaining more domain knowledge. But at least to start with and to play around with few basics, you don't need actually a complete domain knowledge. So that's why I said minimal domain knowledge. And also we also want to scatter this series in terms of software point of view. So being a software developer, and also I want to show different approaches in the software. So in general, what are the approaches followed in the software? So I want to scatter this series of videos on audio and video more from the software point of view, rather than always sticking to the audio video like this. So we should know the basics, but I will be more focused from the software, learning this audio related things from the software point of view. Okay, so that's why I said breaking learning myths on audio and video. So hope you understand my main motivation behind this. And also, as we also want to we'll also put in the GitHub some mini projects related to audio and video. As each video comes up, we'll provide a link, and then we'll be telling, okay, this mini project is available in the GitHub. If someone wants to learn anything, they can check that code. And also you also want to, why we want to keep all these things as a minimal, because to challenge ourselves upfront. Okay, so challenge ourselves upfront means we want to ensure that, okay, uh, like if you learn each feature, like capturing, extracting, encoding, decoding, so if we learn each thing in project by project, we can cover a lot of things and we can learn in depth, and later it will be easy for us to integrate the feature into the actual product, instead of integrating in very fast and then going through all the hardships. We want to divide our entire work into mini projects, and then we will integrate into actual product one by one. So to cover all these aspects, we have come up with this video series. Okay, I mean a video series on audio Okay, so on this note, let's start this. Okay, so basically what is an audio? See, in very layman terms, audio is what we hear to the human ear. Okay, so this human ear has a capability to hear a sound wave. Okay, so sound wave is nothing but when you speak anything in the air pressure, different variations hit across our ears with high pressure and low pressure. Okay, so usually these pressures or these sound waves, in general, it will be captured by an microphone, okay, or a mic, and it will convert that into an electrical signal or called an analog signal called using a sine wave, typical sine wave. Okay, so basically this is the piano, and if you play a piano in the air, sound wave occurs. Okay, so high pressure, high tones, low tones will be there. So these waves will be captured by the mic, and this mic, it will convert these waves into an electrical signal, typically called as uh, analog signal. Analog means that it is continuous in time. Okay, so this is a very basic definition of audio. So now let's see what happens next. So two things you need to consider when you're talking about an analog signal or a electrical sound wave called analog signal. So basically, for any analog signal, two things are important. See, one is frequency and one is the amplitude. See, frequency is number of cycles per second. So in this we have as cycle of we have 1 second. In this 1 second we have two cycles. So this is one cycle until here, one sine wave, and the other sine wave is called second cycle. See, total for 1 second we have two waves, and hence this particular sine wave frequency is 2 hertz. Okay, and one is amplitude, which where the frequency measurement is hertz, and the audio measurement is called, I mean the amplitude measurement is called decibels. So it is often termed as volume, high volume. When you say if you increase the volume, decrease the volume, we are just tweaking the amplitude of the waves. Okay, so and the amplitude for this wave is 1 dB, and here it is for minus 1 dB. Okay, so we will be having both negative and positive frequencies, high pressures and low pressure. Okay, so this is about how we see a audio as an analog wave in real time, and what are the basic parameters surrounding that analog wave. But in most of the times, the operations or the processing of the audio signal doesn't happen in analog. So if you take any microphone, I mean if you take any processor, any microprocessor, typically there will be analog to digital converter. So we can't, I mean that's the basic thing. Okay, so what happens is when you speak, the microphone captures and it will count an electrical wave, and all the information is fed to this analog to digital converter. Okay, and this digital converter, now it starts processing all the data, and then whatever things that needs to be done, it does it, and then it again, after processing, it converts that digital signal into analog signal using a DAC called digital to audio converter. And this again, this analog signal again is fed to the speaker, and then we can hear. Okay, so that's how a typical uh, sound waves are sent from any particular device to the out to the speakers. Okay, it all the operations are done in the digital, so you can also call it a digital audio. Okay, so the main two things which comes under this ADC is sampling and quantization. So let's talk about what is sampling and what is quantization. So I just want to before going into the sampling and quantization, so we just got what is an audio, how audio can be visually seen as a analog wave, and how this or a sine wave for and how this sine wave is converted into digital, and what are the two major things. One is sampling and one is quantization. Okay, so now let's go to the sampling. See, this is the sampling actually. See, each one is called a sample. So a sample is the smallest unit to represent sound. It represents a single position of a microphone. The process of taking samples of analog waveform at regularly spaced interval times is called sampling. So here the sine wave, we are taking samples at different specific times. So let's say we have 50 samples for the here, and then here first sample, second sample. So whatever sine wave we have here, we are converting that into samples. Okay, and total 2 hertz of sine wave for 1 second, we took 50 samples here. Okay, so this is how, and this is how, I mean, this is how each sample is called. Okay, so this each sample amplitude is represented with called quantization. It means like you will be getting the value depending upon the next value and the previous value, and then we kind of average it and we'll get the actual value here. Okay, I mean approximate value. So it's not like the exact value, but almost exact value based on the quantization techniques. So I will not go deep into what is quantization, different quantization techniques we use. So for now you can tell that a certain value is assigned to a particular sample value using a technique called quantization. Okay. So now let's see what are the different terminologies you come across the a digital audio. So now you know a digital audio is nothing but samples. And what is sample rate? So sample rate means how many samples per second. So in the previous way, we can see here you have 50 samples per second, and then here in general, you will be the sample rate will be 44.1 kilohertz. It means like around 44,100 samples will be taken per second. You are losing sound by converting the signal into analog signal, but the beauty is the human ear can't hear the difference. Even though if you miss any information, that is very subtle information, very subtle audio things where which you can't actually audible to the human ear. So that is why most of the times digital audio works perfectly. Okay. So now, so the sample rate, we know, as I mentioned, so what is bit depth? So each sample can be represented by a value. Okay, sample value, and the number of bits you take to represent that is called bit depth. So if you have more ones and zeros, that the way you represent that sample is it means that most of the information is captured. Okay, the higher bit depth means each individual sample has more possible positions it could be in. Yeah, so if you have like floating sample value or any high integer sample value, so if you want to capture that, so if the more the number of bits, the more the data is captured. So like 4-bit, 6-bit, 8-bit, 16-bit, so depending upon the configuration. Okay, so what is called bit rate? See, bit rate is total bit number of bits per second. Okay, here if you have a sample, let's say you have 10 samples, and then 10 in the per second you are processing 10 samples, and each sample is represented as a example 8 bits. Okay, bit depth. So it means like each sample 10 into 8, 80 bits. So for a second we are transferring 80 bits of second, which is of all audio information. Okay, so what happens once after transferring this? All these are, if you write it into a file, you can store that as in the form of binary data, ones and zeros, called raw data. Okay, so this importance of this raw data will come to know about later, but for now you can see audio is a sine wave. A sine wave for in real-time applications, it should be converted to digital, and once it is converted into the digital, you need to know about, in the process of converting digital, what are the things that come into the picture, like sample rate, bit depth, and bit rate. Okay, and this is what you need to know, basic things about the audio in the from the digital domain point of view. But I would also want to talk about this aliasing effect. It means that, so let's say for example, for some reason we have only taken less number of samples. Let's say here we have a frequency of 1 hertz, sorry, 6 hertz. Okay, it means per second we have 6 cycles here, 1 2 3 4 5, we have 6 cycles in 1 second. Okay, so let's, in this case, let's assume we take only 9 samples, 1 2 3 4 5 6 7 8 9, like this you mentioned, 9 samples. So now in order to get the original analog data from these samples, it is kind of giving a different sine wave. So that is called aliasing. Aliasing means we assume it might give us a original analog wave, but here it is not giving the original sine wave, it is giving some other sine wave. So why we need the original sine wave? Because after doing all the process we need to convert this analog digital to analog, right? So to reconstruct we need more number of samples. If you take very less number of samples, you will be losing the data. So uh, what is the threshold we need to maintain at least? What is that samples? So that's where it comes into the picture called Nyquist sampling theorem. So the sampling theorem tells that the minimum number of samples you need to collect is more than twice the frequency. For example, for the standard audio CD, you have a sample rate of 44.1 kilohertz, which is more than twice the typical human range. So this ensures that the audio signals can be accurately represented and reconstructed. Or in much simpler terms, we can say, let's say you have a frequency of 6 hertz. I mean, let's say you have 6 cycles per second or 6 hertz, and so the max frequency is 6, and twice the maximum frequency is 2 into 6, 12 hertz, and 2 into 6, 12 samples. It means you need at least more than 12 samples. Let's say with 20 samples or 15 samples, you can able to recover the thing. So as you shown here, you have only 9 samples. For example, here if you take around 12 to 15 samples or at least 20 samples, you could able to recover the I'm sorry, you could able to recover the entire sine wave. Okay, so that is what is called about the sampling. Okay, so now also talk about, so this is how one thing is sampling theorem only applies for a band limited signal. Band limited signal means here the signal up to certain threshold, it will, the frequencies, the values will be zeros. So below the threshold there will be all the values for that signal. Above that threshold it will, let's say for example if the threshold is 1 hertz, so only it will accept the signal above that 1 hertz. You don't need to worry about this band limiter. Just for the as of now you can just ignore this, but from the simplicity point of view I'm just telling, like you have an analog signal and that analog or sine wave is sent it to the band limiter first, so that band limiter will remove the unwanted frequencies. Okay, and this is now it is sent to digital for converting, and this digital again is converted to analog, and from analog is converted back to band limiter and from the original sine wave. This is how a typical uh, kind of happens in any signal processor or any DSP processor, for in fact any processor. Okay, so now let's see. So now we have, say we are kind of having all these samples, and then we're doing all the processing on the samples, and then we have all the data and everything. So now what comes into this picture of audio codec? So as I mentioned, see, after processing the sample, we are having the data ones and zeros. So if you write that entire information into zero, the size will be very high. Okay, lot of this, it occupies a lot of disk space, and that is kind of a bottleneck for us to transfer the data. So that's why audio codec plays a crucial role in efficiently representing, compressing and decompressing audio signals while maintaining the acceptable quality, and widely used in streaming services and in multimedia application. So see, if you want to design a multimedia application, and if you are heavily processing the raw data, or for in fact if you, for not only any multimedia or any streaming services or any other things, if you want to store the, if you want to process the audio and video data in its raw format, it is very tough. So that's why we need this compressing and decompressing mechanisms called codec. Codec means compress audio and decompress audio. So here we will be focusing on software encoders. Okay, so we are not worrying about hardware encoders. We are only, I mean, hardware codecs. Here we are focusing on software codecs. So an audio codec is a software actually. Typically it is compress and decompress audio data. So you will be saving around 90% of the disk space when you use compressions and decompression techniques. Okay, so now this is what typically happens. You have analog to digital, you encode the data, You send all the information that a multimedia application or any other application, it processes all the required things, and then after that it decodes the data, and then you finally convert the digital to analog again back. Okay, so this is how the typical process happens now with the help of encoders and decoders. Okay, so now in the market, what are the different types of audio codecs available? Okay, see, there are, this audio codecs is categorized into two things: uncompressed audio codecs and compressed audio codecs. So what is uncompressed audio codec? Uncompressed audio codec is nothing but your raw data. You can tell it is at a raw data. It is mentioned as .wav file or .pcm file. It means that you are getting the audio as it is without compression, decompressing, but the file size will be more. Okay. So as we discussed, we to reduce this, we do compression and decompression techniques. Okay. So that depends up. So the audio codecs based upon the algorithms, they're categorized into two things. One is lossless compression and lossy compression. See, lossless compression means that algorithm is designed in such a way that there is no loss. Lossy means that after compressing, a few data is bound to lose. Okay, but that is very minimal and is not visible to the, I mean, not that much audible to the human ear. Okay. So now this in lossless audio formats, so there are different types of things called FLAC and ALAC. So these are two different kinds of lossless algorithms designed by free lossless audio codec and this by Apple lossless audio codec. So if you see any audio files with .FLAC and .ALAC, it means that those audio files have the encoder is FLAC or the encoder is ALAC. Okay, or the audio format is FLAC or ALAC. And coming to the lossy audio formats, we have MP3, AAC, OGG, Vorbis. Okay, it means that if you see any audio file with .mp3 typically and .ac, it means that the encoder in that audio file is MP3 or MPEG or AAC or O or dot, depends on the extension of the file. Okay, so I will not go deep what are these algorithms, why this is called as lossless, and why these algorithms are called lossy, but I'm just giving a very, as mentioned at the beginning of the video, we are just touching upon the points whichever are required to ensure we get our hands dirty on this audio domain, on this audio programming in fact. Okay, so I hope I am clear until this point. So now let's move on. Okay, so what is this? So these are the types of the audio codec actually typically. So it means that see here we have .wav, .flag, and as I mentioned, see .wave is uncompressed, so that's why the compression ratio is not at all compressed, that's why it is 100%. So .flag means that the compression ratio is 61. MP4 is MP3, yeah, it is 63. I mean MP4 ALAC, okay, .mp4 or .m4a, and .wave. So these are all the compressions. So these are not all these files are of audio, few are also video things, for example .mp4 and .ogg, .opps, .mp3, mp4, mpc. Yeah, all these are lossy algorithms, and then you can see here this is the compression ratio is not applicable for lossy because we know that few things are, but this is the decoding speed and encoding speed, and these are all the libraries. So libflag is used. If you want to experiment on this, you need this libflag to be installed, and if you want mp3, you need this libmp3 lame to be installed. So all these are the libraries. So these are the, depending upon the file extensions, you need these libraries to work on this, and also you need these are all the kind of basic comparisons. So you can, so the how to pick the best. So in the industry the best is mp3, but of course I'm just telling this very vaguely, but depending upon, you can go through different pros and cons and you can pick which is best or which is the best audio codec format, so you don't lose the data and very high, and you'll be getting the more quality efficiently. That particular audio format you go, but typically we will use mp3. I mean, that's what my understanding as of now. So now let's jump into the world of FFmpeg now. So as you know, so far we have seen what is an audio, how it can be considered as a sine wave, and why how a sine wave can be converted to digital. In the process, what is meant by sampling and quantization. And in the process of sampling, how many samples we need to collect, what is the threshold, and how Shannon theorem is based upon this threshold. And then also we can see what is the need for codecs. So if you purely deal with the raw data or just the binary data, because of the huge data that comes with audio, it is tough to process, it tough to maintain, it is tough to write applications around it. So that's why we need codecs. So in this codecs, what kind of codecs are there? Lossy audio codecs, I mean uncompressed audio codecs, compressed audio codecs, and in compressed audio codecs, lossless and lossy codecs. So different types and comparisons you have seen. So this gives this might I hope this had given you a little bit into the world of audio. So now we will see from how to play with this audio using FFmpeg. See, I would like to tell one thing at this point. So don't be afraid of this term, or don't be like kind of oh, this is FFmpeg, it is tough to learn. So don't be in that kind of mindset. Okay, even in my beginning days I'm very afraid, but actually after slowly learning things I come to know how if you're thorough with the APIs, it is much more easy to maintain this FFmpeg, I mean to play with the audio files. So it is all about data actually at the end of the day. So typically now you can focus this more on from software point of view. See, typically FFmpeg is a framework. Okay, so why we use this framework? It is just to decode the data, encode the audio data, and to transcode, to convert from one format of the data to other format of the data. It means like MP3 to MP4 or MP3 to AAC. And muxing means you can join different streams of audio. So let's say you can join audio stream from one file and audio stream from other file, or video stream from one file. You can mux it, and as well as you can demux, means separate streams from a file, and then you can filter it and you can play it, and you can, yeah, a lot of things you can do through FFmpeg. So it is a framework basically, and to that framework you need to feed right a correct information. So once the correct information is fed, the APIs does the job for you, and then it will be very easy for us to play around with the streams. Okay, I'm sorry. So FFmpeg typically comes with different kinds of libraries internally. So the main are this, as I mentioned in this slide. So libav util, libav device, libav codec, libav filter, libsw resample, libav format, libsw scale. Okay, so all these are different kinds of libraries. When you, as we mentioned in the earlier videos, we have built all these FFmpeg libraries on our own. Okay, so it is better to build on your own. So you'll come to know what are all the dependencies of the FFmpeg. If you want to add any dependency, how to do it. So all those things you can come across instead of using the pre-built libraries. But as a beginning point, you can still use the pre-built libraries. But I strongly recommend you to build you on your own. Okay, so now let's see what is this FFmpeg looks like. Okay, so typically what is a file? So let's say you have a file, input file.mp4. Okay, so now in this mp4 is nothing but a container. It means in this mp4 file we have three different sets of data: container data, video stream data, audio stream data. This video stream is nothing but this container is nothing but metadata. So it tells what type of container is this, what type of video stream you have, how many streams are there, and what are the specific formats. It is like a blueprint what is there inside the data. Okay, and now we have a video stream and we have audio stream. We can have multiple audio streams, we can have multiple video streams, we can have subtitles. So a lot of things is all packaged and put it in a single file called container, and the format is called mpeg4. So this is how you need to view a an mp4 file. Okay, so by default it is all the files are encoded, and the encoding format, for example, in this file for audio is mp3. It means the audio data is compressed, and the compression technique is lossless, and the specific algorithm uses mp3 format. Okay, and now typically for any FFmpeg, we does, once you read this input file, we decode the audio stream. Once you decode, you will get the original raw data, right? And once this raw data is, you can encode this raw data or a frame, a different audio codec. So for example, I have a file which is MP3, and here I am decoding it, and here I am again I'm encoding with a different audio codec. Okay, so finally after encoding that, it means encoding means you're compressing the audio data, the original raw data, you're compressing it again with a different format, codec format called AAC. And finally, you are writing that entire information into a file. The compressed data, you are writing it into a file. Okay. So here we are decoding and we are processing, and then we are encoding here. So this is most of the things, all the FFmpeg things, it revolves around this concept. But in this process, you need to know what are all the various structures we need to maintain to ensure this process works smoothly. So these are the different structures you will be coming across quite frequently in FFmpeg. AV format, AV codec, AV codec, AV stream, AV packet, AV frame. So these are all the basic structures where the entire information of your video file is scattered, is spread across. So before decoding or before encoding or before, to be frank, to decode or encode, you need to populate the structures smoothly. If you don't populate, somewhere in the process issue happens or some noise adds, everything will be gone. So this sequence is very much important. So I will be covering this sequence now in the next slides. Okay. So this is the sequence I want to introduce such that it is easy for us, and also it ensures that all the whatever data structures we discussed in the previous slide, so all these things will be populated properly and the rest of the process goes smooth. Okay, so see, now you have an input file, and this input file can be video, audio, or only video or only audio. So this input file, from this input file we need to detect the stream of the audio. As you know, a file is nothing but a container, and in that we have video stream and audio stream, and we need to get the audio stream index. And once you have get the audio stream index, what you have to do is you can decode that stream. It means from the encoded data you can get the raw data, but to get that you need to first prepare the decoder. Prepare means you need to, like, kind of prerequisites, all the structures, all the information like streams, and then all the other kind of details like input format, context, codec, all those details has to be populated. Okay, so that block I will call it as prepare decoder. And in prepare encoder block, actually it's like it all depends from the output file. It means like you are taking an MP4 file and you want to convert that into an MP3 file, and you need to open that output file, and you need to give all the options like what codec ID you need, what sample rate you need. So all those details you need to pass in the encoder and you need to make it ready. Okay, so this is like an initialization kind of a thing, in the sense like let's say if it is a hardware, if you want to initialize and all the drivers are loaded, everything, your system is ready, and then you can just from there you can run your applications on your OS. Something similar like that in an FFmpeg, to process the frames, each frame, here frame in the sense like each, like a combination of each sample, process frame or process sample. So in order to process each frame, you need to ensure that all the required details are properly there. Okay, so once that is done, then you can actually go ahead and start doing the things. So let's see what are the list of APIs that are used to make this sequence correct. Okay, so just want to correct one thing here, frames in the sense, see, uh, here we have video stream. Okay, so in the video stream you have actually AV stream, AV packet, AV frame, and like that. So bottom layer is the frame. So once the data is decoded and then it converts to packet and then to frame, so all those this is what the sequence it will be. Okay, so now we will see the list of APIs. See here, get stream index. So first we need to allocate the context for the input file. We use this AV format alloc context, and then after memory is allocated, you open the context, So we open the file, and from that file, if we select, if we use this API AV format find stream info, and these are the arguments, and these are dictionary options. Sometimes you can use null. And once you open the stream, now you will be able to, you can use a for loop and then number of streams. And if the stream is audio, you just populate this audio stream index. So the first block here is you open the input, you allocate the memory, and in that memory you load the input file information, and from that you find the stream info, and you just assign that index to the local variable. Okay, so this is the first and the foremost thing. So the next step in the sequence or the next list of APIs as a part of this prepare decoder block is you need to find the decoder. So we don't know which decoder is there. I mean, what kind of codec is there. So here you need to pass this codec ID. So basically this will be passed. So as you know, from the input file we can get this data, and then or from the file format type, or in different ways this decoder will be found. Okay, so once the decoder is found, you need to call this function called AV codec allocate context 3. So this is a one more API, so which actually allocates the codec context. Okay, so now here see this codec, whatever is returned here, this will be passing it to this function. Okay, so first carefully observe, the first is input format context. So that context we pass it to this open input, and again this context is passed to this I mean this AV format context to this stream. Okay, so you can see in sequence by sequence each structure is getting populated, and here in find decoder you get this AV codec, and this now is passed as input to this, and again we get AV codec context, and from AV codec context we pass that to this here, and here we will be getting codec parameters, and yeah, and finally we send this AV codec context and AV codec and dictionary, all the things to open. So you can see here why I mentioned this as a sequence is because, for example, if you miss this function call, or for example if you this function call, sometimes code may pass, but in only in runtime you might find those issues. But here see the structures is like kind of a pipeline. So the inputs for one structure will give the required output for the other structure. It means like one data is here and then you pass it to here, and then it is giving parameter for the others also, right? So so it's a sequence is there. So all first you need to fill this codec and then codec context. So line by line. So this uses the previous structure information. So all those things you need to fill line by line in a sequential way. Okay. So now prepare encoder. Encoder is bit different in the sense like we need to give more options that I will cover in the next video, but for now I will give you the high level things. See, this is a AV format open, where now we are allocating the memory for the output context. Since the file is not there, we don't open the file, we just allocate the output context, and then here we give the file name also. Okay, and then we open a new stream for it, and inside, so now stream is a combination of video stream and audio stream. Here we will be filling the audio stream details later. So now we need to find encoder. So this encoder we need to pass, and it will check okay whether FFmpeg is supporting encoder. That, let's say if I pass here MP3, it will find that, and then it will try to fill all these structures related to MP3 things, and then this is passed to this and AV codec alloc context 3. So until here, now this AV codec context pointer is for output format. Okay, so in the previous, that is decoder is for input, encoder is for output. Okay, so now the encoder part is ready here, and now here we can open that encoder. So so in the previous slide, see, by the end of this we are opening the decoder. In the main, whatever information it is we gathered from the input file, all those information is filled in the corresponding structures like AV codec context, AV codec, and input format context. These are the three things. And also similar structures should be maintained separately for output format. So here you will open the output context, and then you will additionally you will allocate stream for it, because stream is not there for the output file. We need to create a new stream, and then remaining all structures, so we need to populate as it is. And then by this line we need to open the encode. Here encoder is open. It means stream is not there, but the basic information is required. All the things are put in this particular structure. So now encoder results are ready to process. And finally, this is an optional. If you want, we need to open this file actually. If you want to write the data into the file, or else if you want to just gather raw data, you also need to you can open the raw data file in a different API. I will tell that in the next video. But for now, here you need to open this output file. Okay. So now, see, so far we have done is just populating the different contexts. Okay. So now after populating all the different structures and the context in a sequential way, I'm just reiterating again, you need to populate the structures, you need to follow that particular sequence. If the sequence is not maintained, there are high chances you might be getting runtime issues or the performance is bad. So please ensure that particular sequence is followed. But here I'm just giving a high level information what is about the sequence, but in the rest of the videos I will go through the about each API in detail, and I will tell you what is the desired output we will get if you tweak the parameters. All those details I will cover. Okay. So now see, first actually in the container, now you have in the input file, let's say now we are only interested in the audio stream, and the audio stream is a combination of frames. So you need to iterate until all the combination of packets, to be precise, when all the packets end of the packet. So I'm reading in that packet a frame. Okay. So now in that once I read that packet, and here I will call AV codec receive frame. So this actually return the next frame of a stream. Okay. So this will it will give me the next frame of a stream. Here it is audio stream. Once the next frame is read, you should say audio receive frame. This will give the decoded data. And now once it is decoded, you need to encode it using AV codec send frame. See, remember all these context, output codec context, input codec context, this input format context, all these three structures are already populated as a part of sequence in the earlier sequence. So now once the frame is received, we are iterating it again to ensure all the packets inside that frame we receive. So AV codec receive packet, it reads the encoded data from the encoder, and then finally we write that. I think the comment is bit wrong, but here we are writing that into the frame, into the file. Okay. So first we read the frame, and then we write the encode data into the frame. We receive the frame, and then we receive the packet here, and then we send the frame. So it's like you read the immediate frame, and you decode that frame, and you encode that frame. I mean, you supply that decoded frame to the encode frame. Okay. And now you need to read that encoded data from the encoder, AV codec receive packet. Okay. And then once you receive that packet, you just need to write that packet information into the file. Okay. So this all things goes in a loop unless and until all the frames were read. Okay. Yeah. And this is what you can expect from this series of audio. So we will be going through hands on how to capture a raw audio from the mic and then generate raw data from it through port audio. That is similar to FFmpeg, but more or less the things will be similar. And then we'll be telling PCM data to encoded data using open core AMR. I mean, like how to convert the PCM data to encoded data, and then using open core AMR, that is also one more library. And then we'll do audio raw capture plus encode through open AMR, and then audio raw capture plus encode through FFmpeg. Here you will be seeing all the FFmpeg APIs what I have discussed so far. These three are based upon port audio and open core AMR. The reason I want to go through all these things is just to ensure we provide different how to collect the raw capture and how to do the different things on other things. But yeah, these are like kind of it will give you much more in-depth details actually. See, using FFmpeg, it is a high level APIs, but using these particular libraries we can get in depth. So just to show at sampling level what is happening, I am just following these projects. Yeah, you will get more clarity once we go through the videos. And then finally we mix different PCMs, and then instead of a file we'll be reading from a stream. So we'll also be reading these things. So this will be the series of audio. I mean, the series of videos will be coming from us related to audio. Each thing will be individual project, and we'll upload the code into the GitHub, and we will share the links actually. Okay. See, just to summarize what we have discussed in this video, we have gone through what is audio, what is sampling, what is Nyquist theorem, and how a digital audio comes into picture, and how encode and decode plays a significant role in storing the data, and what kinds of codecs are there, audio codecs, and how we can, from the programming point of view, from the FFF, how we can use FFmpeg framework, and what are the structures are there in the FFmpeg, and what are the list of APIs we need to take care to ensure we convert or we process the data in the desired format. At high level, we have gone through all the details, and also I have told what kind of series we'll be telling. Okay, so all those details we will be capturing. And yes, I think that's all for this video for now. And then if you have any queries and comments, please do, I mean, if you have any queries and questions, please do mention in the comment section, or you can reach to us using our Multimagics blog. Okay, yeah, you can go through this blog. Sorry, yeah, thank you.